Okay guys, let's prove these theorems. Let's make them work for us. The first one we're going to look at is circle theorem 15. This is the one that tells us that if two chords intersect inside a circle, then the products of the lengths of the chord segments will be equal. So A times B will equal C times D. Okay, can we prove this? How do we know this is true? Set up a proof here. Let's go ahead and take a look at our theorem. If two chords intersect inside a circle, so that's our given information. So we got chords, we're given chords RT and SU. Okay, and that is our given. We could say RT and SU intersect at V, right? Intersect at point V. Okay, and what they want us to prove is the conclusion of the conditional, which is that piece that comes after the word then. The products of the lengths of the chord segments will be equal. In other words, could we prove that A times B equals C times D? Okay, good. All right, where's my straight edge? You guys know where I'm going with this. I am hankering to draw some auxiliary lines. I'm going to draw RU. And perhaps as I'm doing this, I should talk about why I'm doing this. I alluded in my other video to the fact, I'm also going to draw this one while I'm at it. I alluded in my other video to the fact that I suspected that these look suspiciously like cross products, right? Okay, and that's just my pattern recognition going off. I've told you guys whether it's music or math or chess, pattern recognition will get you a long way in solving really interesting problems. I think those are cross products, so I'm looking for similar triangles because I know cross products come from proportions, which come from similar triangles. So I'm going to draw auxiliary lines, or I should say really auxiliary line segments. Segments RU and ST. Okay, because 2 points define a line. And we can pick two of those points to pick out a segment. Okay. All right. So how do I know these two triangles are similar? I suspect they're similar. I mean, we have three ways of proving triangles similar. Angle, angle. Remember that one? We got side, angle, side. And then we got side, side, side. Okay. And since we're trying to prove that these segments are equal, we don't really know the segments. So side, side, side's probably out. And side, angle, side's probably out. So I'm thinking we're looking at angle, angle. I'm going to go straight for angle RVU, congruent to angle SVT. We know that's true, right? The measure of angle RVU equals the measure of angle SVT. Or I could say they're congruent. Okay, the reason is those are vertical angles. Okay. All right. Now, I'm going to be so bold as to declare that the measure of angle URT, or I could just say angle URT is congruent to angle excuse me, I got that wrong order. Angle URT is congruent to angle TSU. How do I know that? I know that because angle URT is an inscribed angle in this circle. And angle TSU is also an inscribed angle in this circle, and both of them intercept this exact same arc. I know inscribed angles in the same circle that intercept the same arc must be congruent. Okay, so inscribed angles intercepting the same arc are congruent. Good. I'm going to go ahead and mark that. That's huge. That's huge because that gives me my angle, right? So I can now declare that triangle RVU is similar to triangle, let's get these right, RVU SVT. Similar to triangle SVT. How do I know? lopsided here. Angle, angle, similarity, right? Good. If these two triangles are similar, guess what we know about them? We know that all their sides are proportional. And since I've labeled some of these sides as A, B, C, and D, could I say that A over C equals D over B, right? You got to get them in the right place here. I know side A corresponds to side D in the other triangle because it's the side that's included between these two congruent angles. Okay, so I've got A on the top over here. I've got D on the top over here. And I know side C corresponds to this side B over here because it's the one that's on the other side of the vertical angles. Okay, so A over C equals D over B. How do I know that? That's one of the definition of similar triangles. Triangles are similar, then their corresponding sides are proportional, and bam, there's one of the proportions, right? So could I say now that A times B equals C times D? Yeah, how do I know that? That is our cross products property, right? Say cross products property. Is that what we were being asked to prove? Spot on. QED. All right, next is circle theorem 16. This is the one that tells us that if two secants intersect on the exterior of a circle, then the product of the measure of one secant segment in its external segment is equal to the product of the other secant segment and its external segment. In other words, VS times VR equals VT times VU. How do we know this is true? Let's prove it. Okay, let's go ahead and prove this. I've already set it up. I went through our hypothesis and I pulled out that we've got these secants VS and VT. I should just point out that they intersect at point V. That's our given. And what are they asking us to prove? They're asking us to prove that A times A plus B equals C times C plus D. Okay, where are we going to go with this? Well, I'm going straight for triangles. I see cross products. I suspect similar triangles. I'm going to go ahead and just connect R to T. I'm going to do the same thing with U to S. Okay, I'm going to connect those. Okay, so I'm going to say I'm drawing auxiliary segments RT and US because 2 points. Define a line, and on those lines I can pick off segments. Okay, good. Now I'll tell you what, the first thing I want to go for is angle V. It jumps right out at me. Hopefully you see that sticking out like a sore thumb. Angle V is congruent to angle V. How do we know that? That's our reflexive property, right? Reflexive property. Reflexive property of congruence. Something is congruent to itself. Remember those reflexive pronouns? Himself, herself, myself. Those are reflexive pronouns, things that refer to themselves. This angle is congruent to itself. Good. Now, I also believe that this angle, I'm going to call it VSU. I believe this angle is congruent to angle VTR. How do I know that? Angle VSU is congruent to angle VTR. The reason is those are inscribed angles and they intercept the same arc. They both intercept arc RU. So they must be congruent to one another. Inscribed angles that intercept the same arc are congruent. Good. Okay. Guess what? there's my triangles. Man, that was quicker than I thought. I can now say that triangle VSU is similar, not necessarily congruent. In this case, they almost look congruent, but they will always be similar. Triangle VSU is similar to triangle VTR. How do we know? We've got angle-angle similarity, right? Okay, so if these triangles are similar, do I know that I can set up some proportions, right? Could I say, if I was looking at this triangle VTR, could I say that A over C plus D? I'm going to compare this side to this side. A over this quantity C plus D must equal the same comparison in the other triangle, C over this quantity A plus B, right? Look what I'm comparing there. I compare this side in this triangle to this other side in the same triangle. A over C plus D must equal, flipping over to the other triangle now, C over A plus B in that other triangle. Okay, how do we know this? That's our definition of similar triangles. And from that, could I conclude that A times this quantity, A plus B, must equal C times this quantity, C plus D? Yes, I can, because that is our cross products property. Cross products property of proportions. Is that what we were asked to prove? Indeed it is. Have we arrived at our destination? QED. Okay, lastly, we want to prove circle theorem 17. This one's just a little bit trickier, but same idea. I think we can prove this. This is the one that tells us that if a tangent and a secant intersect in the exterior of a circle, then the square of the measure of the tangent, c squared, is equal to the product of the measures of the secant and its external segment. So c times c will equal a times a plus b. Can we prove this? Okay, let's see if we can prove this. I've restated our given information that we got this secant RT intersecting tangent RU at point R. They want us to prove that c squared equals a times a plus b. And this is a good time to point out that math really builds on what you've learned before. And I'll be honest with you, I don't think I would have seen the pattern in circle theorem 17 if I hadn't first proved 16. After seeing the similar triangles in 16 and knowing that this tangent, we could think of this tangent as just like a former secant, and as he was moving along like this, boom, he all of a sudden intersected the circle at just one point instead of two and became a tangent. And when I picture the pattern of the triangles of the two secants, I can just barely picture the pattern of the triangles that I'm going to need to solve this proof. So let's try this. I'm going to go ahead and draw this auxiliary line segment SU. Okay. Now I know what you're thinking. Where's my other triangle? Don't forget that tangent. You can think of it as a former secant. As he moved along and got to the point where he was only touching the circle at one point, he became a tangent. But tangents and secants are similar geometric figures. So I'm going to draw that auxiliary line segment to try to prove this, because I think there's some relationship between these triangles that I've drawn. So let's draw auxiliary segments SU and UT, okay, because 2 points, again, 2 points define a line. Good. Okay. I'm going straight for angle R. You probably want to get that one out of the way right away, right? Angle R is congruent to itself. How do we know that? That's our reflexive property. And now We just need one more angle so that we could have angle-angle similarity, right? Where's our other angle hiding out? Well, RU is a tangent, and that's significant. There's a theorem we learned that when a tangent and a chord intersect at the point of tangency, they intercept an arc that is equal to twice the measure of their intercepted angle, right? So I could say that the measure of angle SUR equals one half the measure of arc SU, okay? And that is because, what was that theorem? Let's say it was, I'm going to call it tangent chord theorem. But basically, it's that one we learned in our last lesson where a tangent intersects with a chord at the point of tangency, and when they do that, they form an angle that's equal to one half the measure of the arc that it intercepts. Okay? All right, that sounds good. See anything here? Anything jump out at you? Because I'm going straight for angle UTS now. I know the measure of angle UTS equals one half the measure of arc SU. How do I know that? UTS is an inscribed angle, and it's going to equal one half the measure of the arc it intercepts. It intercepts the same arc. Good. This is inscribed angle theorem. Remember, we spent all that time proving those three conditions of the inscribed angle theorem. Inscribed angle theorem. Okay. Well, if both of these angles equal one half the measure of arc SU, then I would say that the measure of angle SUR equals the measure of angle UTS. And that's just by a substitution, right? If both of these equal that, then I could substitute this one in for that over here, and I've got this equation. And if you want, you can go ahead and convert it to congruence. You can say angle SUR is congruent to angle UTS. That's our definition of congruence. And now I get to mark these as being congruent. And that helps me, okay? That helps me see something that I didn't see before. If I flip this triangle over, it looks just like this triangle, only a different size, right? They're similar. I could flip this triangle over here and then rotate it down, and they would have exactly the same shape, just slightly different sizes. Okay, so I think I can go ahead and declare that triangle RSU is similar, RSU is similar to triangle TU. Excuse me, I got to start with R, right? RSU is similar to RUT. Good, we got it right that time. Okay. How do we know? We have angle-angle similarity. All right, we've got our similar triangles. We're in business. Could we set up some sort of proportion here? Let's just look at this triangle RSU. Could I compare side A to side C? A over C is going to equal something. Could I find the ratio of the same corresponding sides in our other triangle, RUT? Okay. A corresponds to side C in that triangle, doesn't it? Okay. And if you want, you can flip those apart and you could redraw these. You could say, let's go ahead and draw this angle, this triangle R. Let's do this. R, S, U. That gives us, that's side A. We'll mark these congruent angles, okay? That makes this side C. I'm going to go ahead and flip over this triangle RUT. Okay, it's just bigger, right? RUT. This might help, okay? And this is our congruent angle. And then in RUT, RU is C units long, okay? And RT is A plus B units long. So this guy here is A plus B, okay? This might help make it a little clearer. So now I can see that A over C equals C over A plus B. A over C equals C over A plus B. Look at that. Since these triangles are similar, we know we can pull out those proportions. This is our definition of similar triangles. Good. And from that proportion, what can I do? Those of you who love algebra know that you can drop back and cross multiply here. C times C gives you C squared equals A times A plus B. Is that what we were being asked to prove? Absolutely. This was our cross products property. All right, I hope you guys found that helpful, proving those theorems. That really brings out what's really fascinating about geometry to me, is the fact that circles and triangles are so interrelated and are such fundamental parts of everything we know about geometry. Hopefully you'll remember those, or you'll at least remember to look for those similar triangles if you ever have to rederive this in the future. And I'm hoping also it'll just help you remember the theorems in general. All right, thanks for watching, guys.